Okay, let me start with a quick introduction about Invasystems. The company was founded in 2016 at Houston in Texas. That's where our headquarters is. And then today we have two development centers in India, one in Pune and the second one is at Hyderabad. The company's focus can be divided into three areas. The first one is production solutions, under which we are focusing on industrial IoT, enterprise mobility, as well as employee engagement. The second area is digital and cloud services. Along with supporting OSI SoftSPI system, we also provide services associated with Microsoft Azure as well as SharePoint. And the third area is enterprise applications. One point I would like to stress at this juncture. All the industries which are mentioned over here, chemicals, oil and gas, power, as well as manufacturing, we do have subject matter experts in each and every area so that we can have effective communication with our customer, understand the requirements, and provide a right solution. Diving into each of those areas a little bit detail, if you look at the second bucket, the data analytics and BI, there are two products mentioned in that particular case. The first one is ProcDNA, which we'll be talking a little bit more in today's presentation. ProcDNA is our advanced data analytics application, and the second one is Diagnis, diagnostic rule engine. When you are dealing with predictive maintenance, there are many scenarios where you come across where you have to set up a diagnostic rules. That particular application goes hand in hand with ProcDNA. Let me share a couple of points about our partnership with Orion. It started about March of 2018. Initially, we started working with the company for providing support for their PI system. That includes global support for managing their AFs, tags, as well as the health check. Like many other companies, Orion has also put together a variety of applications where they have successfully amalgamated data from different sources, like SAP, then proprietary engineering applications. Today, we are providing support for such applications as well. Towards the end of last year, when Orion decided to start their journey on predictive maintenance, we did a presentation on our application ProcDNA, and then we have been selected for the pilot using that particular product, and that's what Jens will be presenting it today. A very quick introduction about ProcDNA. It's an advanced data analytics application, and it has a connector to PI system. What it means, you can seamlessly fetch data into PI system. The application allows you to have two data sets. One for training, that is model building, and the second one is validation. How we have been using this application, Jens will cover that in great depth in the presentation. Along with the statistical information like mean or standard deviation, the application also gives you information about correlation index. Why do you need that? Our advanced data analytics is based on neural network. What it means is there is a concept of dependent variable and independent variable. This particular correlation index guides you in selecting the right variables. Nonetheless, the biggest role subject matter play in our application is the selection of those variables. Last but not the least, when you get data from PI system, you don't want your analytics to learn each and everything what you're getting. The application allows you to select a specific range and then build your model. Here are a couple of screen captures from the application for model training as well as model validation. How this application was used for predictive maintenance at Orion. I would like to hand over microphone to Jens now. He's going to present today one case study, and he's also going to present tomorrow at the panel session the second case study. Jens.
Thank you and good afternoon, everybody. My name is Jens Smits. I'm working for Orion Engineered Carbons, which is one of the world's leading companies producing carbon black. I'm working as a reliability director for Orion. And you may ask yourself, what the heck is carbon black and what it's used for? And that's one of the products, you know, which is currently used everywhere, but nobody knows about that. So if you look around in this room, everything what's black is colored because of carbon black. It includes, for example, cases for laptops, any plastic tires, ceilings, any products made of plastic. Also including toners and printing inks, coatings, and all black products. We are running our business with more than 1,400 employees in 14 plants worldwide. And getting back to OSI Pi, we are using OSI Pi since just one year. We are running OSI Pi with 45,000 tags, actually, with a central asset framework server for all of our plants globally. So this is a globally standardized system for us, which includes process data, quality data, and also ERP data, such as SAP, for example. The partnering with Invasystems regarding predictive maintenance started for us with a reliability initiative Orion started last year, mainly to reduce downtimes on our production units, mainly focusing on better planning to have more reliability and pre-planning phase to do our maintenance. This initiative included two parts, which are condition monitoring as well as predictive maintenance. In condition monitoring, we are trying to implement more sensors which are relevant for maintenance, as well as getting status information about the condition of our equipment. Which we would like to see also in easy accessible dashboards. The predictive maintenance part of this initiative was mainly based on the effort to predict damages based on the reliability sensors we install, but also relying on the process sensors we already have in our plant for production purposes, for example. And one of the main approaches was also to include all that, of course, into OSI Pi. For implementing this initiative, we started a reliability pilot project in one of our biggest plants, which is located in Germany. And we improved the OSI Pi dashboards we already had, and implemented more detailed equipment dashboards to see more details, for example, on vibration analysis of running equipment. But all of our displays we prepared in that pilot plant are always based on a global asset framework standard for all of our plants globally. The predictive maintenance pilot, together with Invasystems, we started in December last year, and we focused on prediction models for our large-scale heat exchangers, which we have and run in all of our plants globally, as well as with rotary dryers, which are also part of our standard process globally. The part with Invasystems included workshops on getting more insight about our process, workshops for better understanding about these processes, as well as preparing the first models, which have been rolled out in May this year. I would like to go deeply into one of these models we created. And one of the examples is the modeling for a large-scale heat exchanger. So these heat exchangers are 2.5 meters in diameter and between 13 and 20 meters high, running at a maximum temperature of 900 degrees centigrade. These heat exchangers are a very important part of our process equipment. And for that, I would like to explain a little bit more how carbon black is produced, that you get an understanding what we are doing and why we are trying to predict a certain process parameter. So imagine at home you have a candle, it's burning, and usually it's just a flame. There should be no carbon black produced. But if you take a cold spoon and hold that into the flame, then you would get something black on that spoon, and that's carbon black. It's pure carbon. And well, this is all about producing carbon black. So it's rather easy. But we do that in a large-scale reactor. So it's a tube about 2 meters in diameter and up to 50 meters long. So that's the reactor down here. We have a small candle burning in here, which is provided by oil and natural gas. So the natural gas is the candle, and the oil gets sprayed into that burning flame. So we have a temperature about 1,200 degrees centigrade in that reactor. And now here's the place where the spoon comes into play. So our spoon, our cold surface, is a water spray which is sprayed into the burning flame. And this is the zone where the carbon black is produced. So we get carbon black, carbon particles flowing in we call that a tail gas flow. So that's a flow with carbon monoxide, carbon dioxide, and other gases. So the reactor produces carbon black. The carbon black gets transported together with the tail gas into the heat exchanger. Which cools down the carbon black and tail gas flow, and in a counterflow heats up the air which is needed to run the reactor. These heat exchangers sometimes have a failure, which is a leakage in the tubes. So because they are running at that high temperature is quite stressful for this equipment. So we may have a leakage in the tubes here. And the leakage in the tubes so by the leakage in the tubes, the carbon black may come into the airflow. So that's because of the pressure differences between tail gas flow and airflow. And in this case, the carbon black gets into contact with oxygen and will start burning. So we get more heat induced in the air preheater, in the heat exchanger. So this will change the temperature level of the air exceeding this temperature, leaving the heat exchanger. So this is one damage which we would like to know in advance, because for obvious reasons we would like to be prepared for a case like this. And to determine this leakage, we are using a KPI which we call the leakage index. And the leakage index is just the ratio between the temperature differences between the airflow and the hot tail gas flow here. So that's for us a major indicator about the condition of this heat exchanger. So this is how a heat exchanger looks like when the tubes are leaking. Yeah? So you see the red glowing part of that heat exchanger. And if you see something like that, it's nearly too late. Yeah? So we want to see that in advance. So our leakage index gets calculated in OSPI. We can see that. We have all the temperatures. There are sensors in that. We are calculating the leakage index. But because the leakage index is differing between different products we run on our reactors, so we are frequently changing the products we are running on these reactor lines. And different products may have different leakage indexes because of different temperature conditions in the heat exchanger. We can't just set a fixed limit, a fixed alarm limit, which would indicate that we get a leakage at the heat exchanger. So this was one reason to see if we could use advanced analytics with ProcDNA from Invasystems to determine which level of leakage index would help us to indicate that we have a leakage occurring here. So if you think back what Ashok explained about independent and dependent parameters which are used for the advanced analytic software, what we do is, or what we did for the model, is we have our leakage index, which is calculated by the temperatures, and we have several parameters which influence the temperature level at the heat exchanger. So this is the oil flow, so the flow of oil which we put into the reactor. The more oil we put in there, so in general the higher the heat is in the heat exchanger. We have the natural gas flow, which will also affect temperatures, as well as the airflow rate going into the reactor for providing air for combustion, as well as the air pressure, the tail gas pressure, which leaves the heat exchanger, and the water flow, which cools down the reaction. So these are our independent parameters, all influencing the dependent parameter, which is the leakage index. And based on the historical data, ProcDNA will learn the dependencies between dependent and independent parameter. So running ProcDNA with our historical data for the dependent and independent variables, we see, and we have a look at the left diagram here, you see the actual measured and calculated leakage index, which is calculated based on the actual temperatures, is the red line. ProcDNA will provide us with the black line, which is the predicted leakage index based on the historical data which ProcDNA uses to learn about calculating the leakage index. So you see it follows the current and actual leakage index quite well. And we see that on the right side, which is the deviation between actual and predicted leakage index. So you see the maximum deviation here is around plus minus 1.4%. So that's rather small deviation we have here. And when you also look at the form of that deviation, it's quite narrow. So that means that the quality of prediction is rather good. So the more narrow this distribution is, the better the prediction is. If we would find a very broad distribution, we would see that the dependent parameters, the independent parameters are not okay. So you need to play around with that a bit to see which are the right independent parameters here. So unfortunately, we were a bit too late with our prediction models, with the rolling out of the prediction models, because before we were able to roll this out, we had a damage on one of our heat exchangers, and that was the picture I showed you before. So in this case, I used the historical data we had about that damage to verify our model with the real-time data here. So on the upper diagram, we see the red line is our actual calculated leakage index. And at that time, there is a leakage starting in this heat exchanger. That was noticed one night, by chance, by the shift personnel, because there was some light in the night where there shouldn't be no light. And that's the point of time where we shut down this line, because we noticed there's a leakage and a damage of this heat exchanger. But when we look at the deviation between the actual and the predicted heat exchanger leakage index, we see that 5 days before we could have noticed that already, because the deviation of between actual and predictive already exceeds 10%. You remember the quality of the deviation while learning the system is 1.4%. So this is giving us, would have given us a lead time from additional 5 days. 5 days might sound short, but the problem is also that 5 days before the damage of the heat exchanger would not be that extensive as it had been. To further monitor these leakage indexes, we are calculating the predicted leakage index with ProcDNA. Also, ProcDNA calculates the deviation, and both of these values are delivered back into OSIPI. So we have all the data available, so ProcDNA learns, creates that model, calculates the predicted leakage index, and the values get back into OSIPI, where we can use them to calculate and to determine what I call a prediction status. So the prediction status is rather simple. It says if the deviation between both is more than 10%, we have an alarm level. If it's less, then we have a warning, and if it's within a certain bandwidth, it's good. This is also calculated in OSIPI, and that means we have a tag, prediction status, which says good, warning, and alarm level. So these calculations go back into OSIPI. We visualize them in PyVision. We have a equipment dashboard here for the air preheaters, for the heat exchanger, which shows the major temperature and pressure values which we need to evaluate our heat exchanger leakage index. It shows the leakage index itself. It shows the leakage index compared to the predicted leakage index. It shows the deviation, and it shows also the status here, including the prediction status. You see that over here. I just included in the asset framework the prediction status, as I said, alarm, warning, and good level, which is here displayed in green, yellow, and red. And we have the current utilization of that displayed in gray. That means our overall limit is 10%, beginning with 10% deviation. We would like to get an alarm here, and this utilization is just calculated as a 100% we are taking the 10%, and currently we have an actual value of 0.01% deviation. That means we have a utilization of this complete warning level from about 1.8%. So that's indicated above. Down here we have the same, just displayed as a time range for the whole prediction. So that would allow us to have equipment dashboards which are accessible for the guys from production to immediately look at that and to see what happens in regard to the leakage index on their air preheaters on the different lines. The way we did that together with Invasystems is of course a bit more what I just explained. So what's required for preparing these prediction models is, at first you need to have the data. So if you have OSPI, you hopefully have all this data available. You need to have these data available also in a time range from about at least half a year, maybe more, to get enough historical data to train your system and as well as to test the data. You need to cleanse that data because you should not include any failure data, because you don't want to train your model with data which already indicates a failure. So that would mislead the model. So we implemented the ProcDNA application together with Invasystems. We deployed prediction models for heat exchangers as well as for our rotary dryers. We will speak about that tomorrow during the panel session. And the rotary dryer, for the rotary dryers, we are predicting the bearing temperatures of the rollers where the rotary dryer sits on. So that's a completely different application, but which proves the practicability of Invasystems ProcDNA, because in my eyes, the main opportunity we have and the main advantage is that we don't need a physical model for the prediction. So for ProcDNA, it doesn't matter if you are including the moon phases or whatever, as long as it has influence on your parameter which you want to control. So we deployed all these models. They are linked into OSPI. They bring the data, the results into OSPI, and they provide us some extra lead time to be prepared about the damages. So it doesn't help, of course, to prevent these damages, because especially leakage index will indicate the leakage once it happens. So it doesn't stop the heat exchanger from leaking, but for us the main important part is that we get some more time to be prepared, and that's our main outcome of this project. And as well, the main focus for us was also to bring all that into OSPI, to have one system to look at and to provide to our shift personnel to look at the air preheaters to be prepared what happens here. Yeah, so this is for us a major improvement, and we are continuing working with Invasystems also with other equipment types. And yeah, we are hoping that we still will have some more advantages from that system. Yeah. Thank you very much.
Thanks for your time.
Thank you. And if there are some questions, the mic is over here. So,
yeah, there's one question over there.
Okay.
Hi, Carl Gerard, Shell UK. Can you just say a little bit more about how you actually write it, about how you do the real-time prediction calculations? Are you doing the calculation in AF and writing it to Pi, or are you doing it in some third-party system and writing it via AF?
Okay, the predictions are done using ProcDNA because you are collecting data in Pi systems. Once you build your advanced data analytics model, that is, then the system is deployed in the real-time environment, the ProcDNA. As soon as the data hits OSPI, then we basically get the data into ProcDNA, perform all the calculations. Now you have one number first is the predicted number. Those results are sent back to Pi system for the system of record. Then we compute the percentage deviation and then generate the alerts as defined in Pi system. Today we are doing the predictions after every 5 minutes, but obviously that frequency is configurable. Any other question?
No, there's another.
Chuck.
Could you hand over the mic, please?
Pierre Bernardi from Total. If you have to update your model, meaning your prediction model, who is doing that? Your company or
Well,
the supplier?
it may happen that the implemented prediction model is not up to date anymore because the process conditions change overall, for example. So if we would exchange one of our heat exchangers completely remove and build in a new one, you would need to retrain the models because the conditions are completely different. In this case, I would download the historical data. Well, in this case, we don't have any, so we need to wait for some time to have new historical data. So I would download that. I would feed that into ProcDNA, and we are even able to provide these models into the ProcDNA server and also do the connection into OSPI on our own. We usually don't do that because I don't want to do all that work, so we have some support from Invasystems here, but we would be able to do that on our own. So the training and the testing of the models is done by us. So we do that. Okay, there's another question down here.
More question?
Okay, so fortunately and unfortunately, you had the problem with the heat exchanger, but it did help you to have ranges for the alarms. If you hadn't had this problem, in which other way will ProcDNA or the Pi system help you with this kind of notifications?
Well, if you don't know how the damage looks like and what it causes in regards of the data you have, well, you don't have any approach to do that. You could try to find something where you think it might indicate a damage. But you should know, at least have some idea about how the damage affects your sensor data, what will happen with the data. Because ProcDNA has no physical model about these equipment. So I think you have no other choice other to know what the damage means to your equipment and to your sensor data.
What I would like to add to what Ian said is that is where the physics comes into picture. Say for example, if you have a fouling problem in your heat exchanger, you can start looking at thermal resistivity as one of your variables. Thermal resistivity will give an indication about how your heat exchanger is performing. Then that becomes your dependent variable. Then you figure out all your independent variables depending upon your process. That's exactly what we did in case of Orion as well, which we are not presenting this time. But for fouling, we use thermal resistivity. For tubing leaks, we use leakage index.
Thank you.
Okay.
Okay. Okay,
Alright.
if there are any other questions so far, then I would like to thank you for paying attention.
Thank
at
you
least
very
if,
much.
if that was the last presentation for today. Thank you very much and have a nice evening.
Thanks
Goodbye.
very much.
Thank you.